I will be telling you a bit about abstract interpretation in my lecture series. I have a lot of topics that I can cover. We'll see how far we get, depending on the time. Feel free to ask any questions at any point. The ones that I don't get to cover in the lecture, you read them on Slack, I will get to them later after the lecture. Just before I get started, I just wanted to tell you a bit who I am. So I was born in this little city in Italy. I put my year birth, because I'm not yet 40, so I thought it was okay. I studied essentially all up to the PhD. I did all my studies in Italy. And then I decided to move to France for my PhD, essentially to work with the inventors of abstract interpretation. Just at the end of my PhD, I did a short internship in the US at NASA and CMU. And then I did a postdoc at ETH in Zurich, a little bit more than 3 years. And since then, I am a permanent researcher at INRIA in Paris. So, what is abstract interpretation? I will get to it in a second, but it essentially is the reason why we do abstract interpretation is a way to avoid the cost of software that breaks down, that doesn't work. Especially depending on the applications in which the software is used, it can be very costly. It can kill people. And so to avoid all of these problems, so all these applications, we call them high stakes or safety critical and all this. I will get to machine learning later on, so it's not necessarily high stakes at that point. It's going to be also applications that have a sort of an impact on our lives. But all of this, essentially, all software that has an impact on our money or our health or our safety and security, if it doesn't work, it's problematic. And so we need some sort of guarantee on the behavior of this kind of software. So ideally, what we would like is that we have our piece of software, we have some requirements that we expect from the software, we feed it to a piece of other software that will automatically tell us whether this original software satisfies the requirements or not. As you know, this is not something we can do automatically for all possible kinds of software. And so there are different ways of compromising on this. This is just to place abstract interpretation essentially in the realm of formal methods. So one first compromise is on how automatic this process is. So here we can do deductive verification. We can be very expressive in the kind of requirements of the software that we can prove. But on the other hand, the automation gets lost because it is for us to interact with the prover to guide essentially the proof. The other way to compromise is to do model checking. Here the compromise is in the sense of the kind of software that we analyze. We don't analyze the software directly, but the model of the software. We can be sound and complete, so we can verify, we can find bugs, but it's with respect to the model, so then the question becomes whether the model is faithful to the original software or not. And finally, it's abstract interpretation, what we talk about in the rest of the lecture. And so there are other kinds of static analysis that I will not talk about. So when I talk about static analysis, I really mean abstract interpretation. And here the compromise is on whether we can actually find bugs. So we analyze the software as it is. We do it automatically, but it's correct in the sense that when we verify the software, it is verified. But when we cannot verify the software, we raise an alarm, and this could be a false alarm. It's not necessarily a complete test. Yes.
So it has false positives but no false negatives?
Yes. Yeah. Okay, before I get technical, we will get very technical later on. I just wanted to give you an intuition. So if there is anything that remains to you from these lectures, should be it. So imagine you're buying some clothes. You're in a shop, you want to buy some clothes, t-shirt, pants, whatever, but you only have $100. So what can you do to figure out if you have enough money? You are the cashier, you're supposed to pay. What is one thing you can do quickly? Yeah.
Sum up the costs of pins you're trying to buy?
Yeah, but it takes too long, right? Unless you're super fast. Yeah.
It's like round up the
Yes, you can do a rounding up. So 9.95 or whatever it is becomes 10, 35 and so on, it's 40. So you add up the rounded up prices. Here you get to $90. Oh, sorry, I wrote euros, but whatever. And so it's okay, you have enough money. But now let's say you only have $80. And now you have an alarm because you may not have enough money, but in fact this is a false alarm because you do have enough money, in fact, but you don't see it because you're rounding up, has rounded up too much. So essentially, your card with the clothes is your software. And now the software has a lot of characteristics, right? Your clothes have a lot of shapes and colors and materials and so on, price. So they have different characteristics, and in fact you don't care about all of them. You only care about one in particular, so you have one property of interest that you want to reason about. In this case here it's the price. So you have a specific property of interest. Based on that property of interest you build your abstraction. In this case is rounding up of the prices. And this abstraction is what we can say sound. It's correct. Whenever you say that the property of interest is satisfied, it is actually satisfied, but it's not complete. So this is the whole intuition that we're going to basically follow through the rest of the lecture. You essentially do abstract interpretation every day in a way. So, Patrick Radiocuso invented abstract interpretation, and then of course a lot of work went into it. And now I will present some of it to you, starting from the basics, and the basics can be quite hairy. So this is my son meeting Patrick Cuso, a couple, last year. I hope you will not have the same reaction as him going through this lecture. He was not happy. Anyway, so what do we do with abstract interpolation today? Actually, it's very used every day. Is now integral part of the development of safety critical software in the avionics industry, at the European Space Agency, is used in the automotive industry and so on. And there are some software companies that within their development processes, they use static analysis in various forms. So what's the plan for the lectures? Well, we're going to start with the top left corner. So this is going to be the foundations which we're going to do today. Hopefully to the end of it, we'll see. So this is the most important part. The others are essentially, we build on top of it. And actually, so I do 4 parts, but there are actually 5 parts. Because we're going to go first in the top right, and then bottom right, and then we're going to go bottom left, and then bottom right. So this complicated part is going to come twice, depending on the time, how much time it takes. And I will tell you what the titles actually mean, you will see. But so for now, we start with the top left, which are the principles of abstract interpretation. So to start, I will use roughly, not super consistently, but I will try to use this sort of language syntax. We're going to have expressions. So we're going to have variables, constants. This one is going to be a non-deterministic values choice. So there is no probabilistic stuff here. It's all the normal numbers. It's just that we have some choice between a range of numbers, essentially. And then we can do operations between these expressions, binary operations, unary operations, and so on. And then the statements are going to be very simple. We have assignments, so we can assign an expression to a variable. We can have a if conditional statement, so we can do something conditionally to the truth of an expression. We can do loops, and we can just concatenate those sequences of statements. And I put labels before and after statements. Sometimes I skip some of them because I don't need them, but they're essentially convenient to say what happens at a specific point of a program. So as an example, for instance, we're going to use quite a bit this kind of program. Here, this is the modulo. We're going to compute, it's a modulo of A. It's A modulus B is saved in R, essentially, I think, if I recall correctly. So we have essentially a number that we pick in a range, it's a positive value between 0 and plus infinity. B, also a positive value, then we assign a Q to 0 to Q. A to R, and then we have a loop where we decrease the value of R by B, and we increase the value of Q by 1. So this is roughly the example that we will use. We will get back to it many times. I just need it as an example. It's not particularly interesting or anything. Okay, so how do we do static analysis by SL interpretation? Roughly, it's a 3-step recipe that we follow. It's not linear, and also it's not in the order in which you see it. It actually goes from the bottom to the top. And it's not something that you do step by step, but sometimes you will go back and forth between the steps. But essentially, first of all, you need to formalize essentially the model. You need to build a mathematical model of the behavior of your program. This is going to be called the concrete semantics. Then, at this point here, this one will be specialized to the property of interest that you care about. If you remember, we said that we don't care about all aspects of the computation of a program. We care about a specific one that depends on the property that we want to prove about it. And so we're going to build, especially in later parts, but we're going to build essentially concrete semantics that are specific to the property that we want to reason about. And here will still be sound and complete, but we cannot compute anything with them.
Yep. So the concrete semantics for the shopping mall example is instead of having the pants and the shirts and whatever, you just have the receipts, you just have their prices?
Oh, no. So the concrete semantics is actually the pants and the t-shirt and it's all of those things. And then actually I will go back to the analogy step by step, so you will see the pieces. But after that, you cannot compute anything with it, so you need to build something that is computable, your abstract semantics, using some abstract domains to do the actual abstraction, and some algorithms to manipulate these abstract elements, to actually do the sound but not complete analysis in practice. But this is still sort of, there is nothing that works in practice, there's nothing that is implemented. So then you have the implementation, and the implementation actually can change how you design your abstraction in a way. Because you will see that sometimes the abstract semantics that you have designed will not work in practice, and you have to go back and redesign things and so on. I will do it later, you will see. But the first part, we have to start with the concrete semantics, which is, in the analogy is this, the whole thing. So you have your clothes with their colors and shapes and prices and whatnot. So we have we model everything from our program, and then we try to abstract away what we don't need. So let's model everything at first. So we have our expressions, so we have to build the semantics of expressions. So essentially, we're going to take an environment, so a mapping from variables to values. I will take integers for simplicity. And so we take an expression, we take a memory state, what we call, or environment, and we evaluate the expression in that state. This will give us a set of values. So for a variable, it's going to be whatever value the variable has in that state, in a set, in a singleton set. Constant is the same, it's just the constant in the set. Here we have an actual set of values, because we have a range, so when we evaluate it, we take all values, range of the values between in that range. And then for the other expressions, the same, right? We evaluate the sub-expression, and then we do the operation on the values that we obtain. All good? It's rather standard so far. So this is for expressions, and then we have to model the statements, of course. So we have what we call a transition semantics. So essentially, this is the simplest model. So we're going to model basically programs as transition systems in a way. So we're going to have the executions of the program will be modeled by transitions between states. So the states are going to be these memory states, these environments, at a specific label in the program. So we're going to have this location in the program, some state, and so on. And then there's going to be a transition relation, so essentially a pair of states, which means that there is a transition from one state to the next. So in the program, I removed these choices because it didn't fit in the slide. So we start from program point 3. This is the example from before. And here I show you some of the transitions in the system, right? So this is a state, for instance, where A is 0 and B is 2. And then we can move to this state at program point 5, and this state, and so on. So this one is the state where R is going to be 0, And then this program point 6, we test if R is greater or equal than B, which is false, so we exit the loop right away, we go to program point 10, and so on. All good? Yeah.
So the transition relation, it's not a function. You can go.
No, it's a relation. Yeah.
Okay.
So you could have actually non-determinism, so from a state you could go to different states. Not in this particular case, but. Okay, so then finally we can define the actual transition relation. So for instance, well, I could have showed it step by step, but well, for statements, for assignments here, for instance, we have a state. Well, actually, okay, I'm doing it. Okay, I did it. I split the things a bit. Actually, this essentially I'm giving it an environment, but it should have been actually a label and an environment. But okay. But so for an assignment, for instance, whatever the state we give it to, the memory state, the transition is going to be basically going from L1 with whatever memory environment we have to L2 after the assignment. So L1 is before the assignment, L2 is after the assignment, with the environment modified so that we X now maps to the value of V, which is the value of the expression that we assigned to X. So it's very sort of verbose in a sense. So we have basically to note all the transitions that we do in the program. For the if, we have various transitions. We go from either from L1 to L2 or through L4 if the condition is not true. So we have the two cases. We evaluate the condition. If it's true, then we go inside the body of the if. If it's false, we go outside at the end of the if right away. If we went inside, then we have to go, we evaluate we have to do the transitions from S. So from L2, we have to go to L3, and then from L3, we have to go to out to L4. So we have the two paths through the brain state. And for the while is similar, except that now from L3, we go back to the head of the loop. And from the head of the loop, the condition is false, we go out. So it's the same kind of mechanism. And here for the sequence, we just do the transitions from the first, and then we do the transitions from the second, and so on. This is the starting point, roughly. And then based on this model, we actually can build a whole hierarchy of semantics. So a whole hierarchy of models of the behavior of the program, which have more or less details depending on what kind of property we want to reason about. So in fact, the most common ones are the ones at the top, what are called state semantics. And we're going to start from those. But actually then we're going to go deeper to this tip of the iceberg at the bottom, which is the most general model. This one at the bottom is called the maximal frame semantics. We will define it later on. But yeah, this is the most general model of a program that we can use to verify any property that we want. And the simpler properties actually can be verified by the simpler semantics that are here at the top. So we will get to them step by step. So we start with the first one, this forward, it's called the forward reachability semantics. It's a state semantics. Essentially, we will collect all the states that we can reach from a set of initial states. Before I can actually define it, I have to give you a bit of some definitions that I will need. So I have to do a little interlude with definitions. I have to start with partial orders. I don't know if you have seen them already, but essentially a partial order is a relation. It's a binary relation on set. And it's a partial order when it has three properties. First of all, it's reflexive. So essentially, it holds on the same element. It's antisymmetric, so if you have two elements that you can compare, so one is smaller than the other, and the other is smaller than the one, then they are the same elements, and it's also transitive. So this is called the partial order. And now if you take a set and the partial order on that set, this is called the partially ordered set or a poset. As an example, we will use this a lot. The power set of a set is an example of a partially ordered set. And in particular, we will use a lot of this power set of the set of program states, for instance, ordered by set inclusion. This one is an example of partial order set. If we take this example, let's say we have elements A, B, and C. We can write the poset in this sort of a diagram. It's called the Haas diagram. So you have the least element here, the greatest element up there, and all the other elements in between. So all these lines here mean that this element is smaller than this one. This one is smaller. So these lines are the partial order relations, essentially. Okay, then finally, last bit of definitions that I need before I give the actual definition of the semantics are the upper bounds and the least upper bounds. So if you take a set X, this element here, so this set contains B and C. This element here and this element here are called the upper bounds, so elements that are bigger than the set. And this one is the least upper bound, the smallest of the upper bounds, essentially. Okay, this one here, this is called also bottom. It's the least element of the poset. And this is also called top, and it's the greatest element of the poset. So when you see these symbols, top and bottom, these are the, yeah.
Every concept having a upper and lower bound?
No, I will get to it later. Yeah, they don't. Not in general. In this particular case, yes. Actually, this is a complete lattice, in fact, but we will get to the definition later. Okay, so finally we can define the semantics. So this semantics is going to be a set of states, and these are the set of states that are reachable from another set of states, I. So this is the set of states I, so we have essentially a sequence of states. The first one is in I, and all the other ones are connected by the transitional relation of our program. And we collect all of the sets that we can reach. Yeah.
I have a little bit of trouble understanding the transition relation, like 5 slides ago.
Okay. You can also ignore it if you want.
Oh,
It's not super fundamental to understand everything about it, but we can get over it again if you want. It's also a bit messy, my definition.
I was wondering what the labels were doing.
Oh, so the labels is basically, let me go here for instance. Yeah, the labels here, you see there are labels in the program. So I'm basically saying where I am in the program, sort of. So I'm basically saying, okay, I have a state. So this is my state here, a label and an environment or memory state. And this is the next state that I reach. So basically when I do this, I wrote arrow, but it's supposed to be, the pair of the two states. I will fix this line before. Let's ignore this one. It will make more sense the other ones. Okay, so it's not super important. You just know that there is a relationship between states that can be one the successor of the other. That's enough. Okay, so in the example, for instance, if this is I, then all these orange ones here are the states that we can reach from that I. All good? Okay, now there is another bit. So in this hierarchy of semantics that I'm trying to present you, it's more convenient to actually present or define the semantics as a fixed point operation for various reasons. In particular, I will show you in a moment, because there is a theorem that allows to derive one semantic to the other when they are defined in a fixed point form. So we're going to get to fixed points also. I will show you. So fixed points are, we have a poset, we have a function that works on the set here. So a fixed point is an element that is, basically when you apply the function, you get back the same elements. This is called the fixed point. We also have interesting things that we need are these prefix points, so these elements that are smaller than the fixed point. So just, you have the fixed point and the ones just before are the prefix points, and the postfix points are the ones that are larger than the fixed point. So there is a fixed point somewhere in your function, and you have elements that are after and elements that are before. Okay, then there's the set of all the fixed points of a function. Obviously, we can define it. And within the set, we can define the smallest fixed point, the least fixed point, or the largest fixed point, the greatest fixed point. Most of the time we will work with this least fixed point operations. So we will try to find the smallest fixed point of a function. Well, not try to find, we will define the smallest fixed point of a function. In some definitions later on, we will also use the greatest fixed point. Oh, we will get to it later. So, if you want to define the forward reachability semantics in a least fixed point formulation, what we have is basically this. We have a least fixed point starting from the empty set of states. We will proceed, the iteration will proceed in the subset inclusion order, so we will make the set bigger. And the operations that we will do, the function that we will apply, is this one here that takes a set, adds the initial set of states, and then takes all the successors of the state.
Oh, it's just fine.
Okay, no, I thought I saw a hand, but okay. Okay, and the definition of post, the formal definition is here, but really, okay, when you have a state, you take the successors of that state. One important bit is this order here. When we use the fixed point definition, this is called the computational order. It's just different from, in general, from an order that we will define later that allows us to reason about the precision of the abstractions. This one will be called approximation order. So we have to, in some cases, we have to keep those two things distinct. We will see later. But to give you more of an example, again here, this is I, and when we do the fixed point, we start from I, and then we add all the states that we can reach in a fixed point operation. Okay, just to annoy you a little bit, I'll give you the denotational formulation mainly because I will use it later on. So when we have a sequence here, so we have a set of states that we have computed so far. Yes, we will go through the first statement here. We'll get the reachable states after the first statement, and then we will feed this to the second statement to get the reachable states after the second statement. So it's going to be a forward kind of semantics. We will also see backward semantics in a moment. For an assignment, it's similar as the transitions, but now we just collect the states that we reach. So we start with whatever state we have in S, depending on the value that we evaluate from the expression. The next state, the set of states that are reachable from that point is going to be the set of states L2 at label L2. So after the assignments, and the states will be the ones before the assignment, this row here, modified where X has the value of the expression at the evaluation. Yes, when I do the denotational formulation, I'm basically collecting the states that are reachable right after the statements or right before the statements, not collecting whole things. There is a sort of pointwise lifting of the definitions. That's why there is not a S union in this one. Okay, for the if, it's similar as before, right? So it's just a bit more involved because we have to go from L1 to L2 if the condition is true, and then we have to evaluate the statements. We have to get the states that are reachable after the statement inside the body, and then we have to get them to label 4 essentially. So it's a bit involved because of this, because I put a lot of labels. We could have skipped the labels. And same here. So here we are, the states label 1, where when we evaluate the expression is false, then we get to label 4. Okay, for the loop, it's going to be the fixed point in here. The fixed point at label 1, and the condition, and then the ones, because we have to basically get the statements reachable after, the states reachable after the statement. So we have to do the fixed point for the states that are reachable at the loop head, essentially. And then from those, we take the ones for which the condition is false, and we put them on label 4. Yeah.
So I think I'm confused. What happens if the while loop diverges?
Oh, no, this is just the states that are reachable.
Right, but why does the fixed point
It's it can be an infinite object, and it's okay. It's not something you can compute. It's just a mathematical object. Could be, but it will be an infinite set of states. Okay, this is for the forward reachability. Now we go to the backward reachability. It's very similar. Now we are the states that reach a certain state. So set of states F. So the definition here now, we have a sequence of states where we start from S and then we end up in F, and everything is connected by the transition relation. So in the example here, for instance, this is our F. When we go back, we just follow the arrows backwards essentially, and all the orange states are the ones that we can reach. And again, we can also define it as a fixed point, but now we're going to start with also as an empty set and so on, but we're going to start going backwards. So we take all the predecessors of a state, set of states, on this pre-transition relation. So here, in the example, similarly, we go back and we from F and we color in orange everything. And so for the rotational formulation is very similar as before, but now we go backwards. So we start with a set of states, S. We first go through S2, and then we go to S1. And all the others, they also are, they also go backward in a sense. So here, we take the states, the reachable states are the states L1, so the ones before the assignment. And those are backward reachable if the ones after the assignment are in S, essentially. And the rest is similar, you just have to do all the computation backwards, in a way. All good? Yes?
I understand the sort of like, these could be infinite objects. In the specification you've given, where we're working over the integers, I think, are we just assuming all of these are infinite in some sense that we're providing an infinite number of input that we're considering?
It can be infinite,
Okay.
yeah. It's no. It's really, again, these are all just mathematical definitions. We're not computing anything with them.
Okay.
It's okay if they're not computable. It's okay if it takes an infinite amount of iterations to reach the limit, the fixed point. It's all like, we don't do anything with them. We just have an object that we define. And then to actually do something, really, we're going to need to do abstractions afterwards. But, yeah. I have to check that. Okay, good. Okay, so now we've covered the two parts at the top. These are the easy cases, essentially, the ones that you see most of the time. And I'll try to get you to the bottom of this iceberg. Mainly because you will see later, depending on what kind of property you want to prove about your program, you have to decide basically where you stand. Most of the simple properties are up here. The more difficult ones, you have to go down here. Okay, so let's go to what we call the prefix trace semantics. So we're going to work with sequences of states. So a bit of notation. This is an empty sequence. This is a sequence of length n. This is the set of sequences of